Welcome to this explainer. Imagine you're setting up a crucial power quality experiment. The datasheet for your brand new instrument proudly boasts 16 bits of resolution. Honestly, it sounds extraordinarily precise, right? You hook it up, trusting those numbers to capture every tiny nuance of your signal. But what if those 16 bits don't actually mean what you think they mean? Well, today we're going to look at exactly why a 16-bit meter can still give you a remarkably bad measurement. In university laboratories and power quality research, we constantly run into this massive practical tension. If you're monitoring a main feed, you absolutely need a measurement range large enough to avoid clipping the fundamental current and all those large, unpredictable transient peaks. So in our fictitious example today, we're forced to use a 300 amp peak-to-peak input span. But here's the catch. That massive 300 amp range can make a tiny 0.1568 amp target harmonic incredibly difficult to actually resolve. You're basically stretching a giant canvas just to paint a microscopic dot. Okay, let's dive into this. The big question we have to answer is, does a 16-bit instrument automatically provide 16-bit accuracy? It is such a common and, frankly, costly engineering misconception to assume that bit depth alone guarantees your measurement accuracy. Today, we're going to prove exactly why falling for that assumption is a total trap. To pull this misconception apart, we're going to do a forensic teardown of a standard measurement chain in 5 steps. We'll start with ideal resolution, move to effective resolution, factor in sensor uncertainty, introduce input noise, and wrap up with resolution versus accuracy. Before we jump into the math, let's just quickly lock in our terminology. An ADC, or analog to digital converter, is essentially the electronic heart of our instrument. It's the component that takes our continuous analog input, our physical real-world current, and chops it into a discrete, numerical digital output that a computer can actually process. Another vital term is the LSB, or least significant bit. You can think of this as your ideal code width. It is the absolute smallest physical change your ADC can theoretically detect, calculated simply by dividing your full-scale span by the total number of digital codes available. This represents our absolute best-case limit. All right, step 1, ideal resolution. Let's start with the absolute perfect mathematical scenario. The formula for calculating total digital codes is 2 to the power of our bits. Since we have a nominal 16-bit instrument, we substitute that in, 2 to the power of 16. That results in 65,536 possible digital codes. Honestly, that's a massive number of tiny increments to measure with. Next, we need to find our LSB size, our ideal code width. The formula is our span divided by our total codes. So we take our required 300 amp span and divide it by those 65,536 codes. The result is 0.00458 amps per ideal code. That right there is the smallest theoretical step our instrument can take. Now, let's apply this ideal step size to the tiny signal we actually care about resolving. The formula is the target harmonic divided by our code width. We substitute our 0.1568 amp target and divide it by 0.00458 amps per code. The result? Our tiny harmonic spans roughly 34.25 ideal codes, 34 distinct data points to map out that little wave. Sounds like plenty of resolution, right? But remember, this is a mathematical fantasy. It establishes resolution, sure, but definitely not reality. Moving on to step 2. Effective resolution. To face reality, we have to talk about ENOB, or the effective number of bits. This is a measured indicator of the ADC resolution that actually remains usable after the instrument's own internal noise and distortion take their toll. I literally cannot stress this enough. ENOB drastically reduces your usable resolution, but it is still not an accuracy specification. Let's see just how much damage ENOB does to our beautiful math. Let's say our fictitious lab instrument has a 14.5 ENOB specification. The formula for finding our actual effective levels is 2 to the power of our ENOB. We substitute 2 to the power of 14.5, which gives us approximately 23,170 effective levels. Just think about that for a second. The physical reality of the silicon just wiped out over 40,000 of our codes. Because of that, we have to calculate a new, realistic code width. The formula is our span divided by our effective levels. We take 300 amps and divide it by 23,170. The result is 0.01295 amps per effective code. Because we lost so many codes, our measurement steps just got significantly wider and clunkier. So let's check our target harmonic again with these new, wider steps. Target harmonic divided by effective code width. We substitute 0.1568 amps and divide it by 0.01295 amps per code. The result? Our target harmonic, which used to span 34 steps, now spans only 12.11 effective codes. Honestly, this brilliantly illustrates the danger of reading just the top line of a manufacturer's spec sheet. We plummeted from 34.25 ideal codes down to just 12.11 usable effective codes. The instrument's own internal limitations wiped out a massive chunk of our viewing window. And the craziest part? We haven't even factored in the physical sensor sitting outside the instrument yet. And that brings us perfectly to step 3, sensor uncertainty. We have an external transducer making the physical measurement, right? Let's look at its stated uncertainty bounds. The formula provided by the manufacturer is plus or minus 0.5% of the reading plus a fixed 0.02 amps. Let's substitute our exact values. That's 0.005 multiplied by our 0.1568 amp target plus the fixed 0.02 amps. The result is an uncertainty bound of plus or minus 0.02078 amps. To put that in perspective, that is 13.25% of our entire target harmonic. That physical sensor uncertainty alone is larger than one entire ENOB-equivalent code. Your bias is literally eating your resolution. Step 4. Input noise. The real world is messy, and random external variation is constantly superimposing itself onto our measurements. Let's say our instrument has an input noise specification of 0.01 amps root mean square. Let's see how much of our signal that noise obscures. Input noise divided by target harmonic. We substitute 0.01 amps divided by 0.1568 amps. The result is 6.38% of the target harmonic. Now, this isn't a fixed bias. It's random variation making repeated readings fluctuate. This 6.38% means you can't just take one reading and trust it. You need careful filtering and statistical averaging just to interpret what is real. Step 5. Resolution versus accuracy. Let's pull all these threads together. Nominal bits just describe available digital codes. ENO describes the usable digital resolution. Sensor uncertainty describes possible measurement bias. And noise describes random variation. None of these single numbers gives you your accuracy. If you confuse them, the practical consequences in a power quality lab are severe. With a weak chain, you might completely miss a real harmonic because it's swallowed by uncertainty. You might mistake random noise for a valid signal. Or worse, if you're operating near a strict laboratory acceptance threshold, these limitations can completely alter your apparent conclusion. To protect your data, you have to evaluate the entire chain holistically. Here are 3 vital questions you absolutely need to ask. 1. What is the smallest signal of interest you actually need to resolve? 2. What input range is truly required so you don't unnecessarily overscale your span? And 3. What complete measurement chain uncertainty and noise specifications apply to your exact setup? A nominal 16-bit label sounds incredibly precise, but as we've just seen, it absolutely does not guarantee 16-bit accuracy. You cannot just combine these errors into a single magic accuracy number without a strictly defined statistical uncertainty model. So I'll leave you with this to think about as you head back to your lab benches. Does your 16-bit label hide the mathematical truth of your measurements? Audit your instrument chains, rigorously check your spans, and never take a bit depth specification at face value. Thanks for joining me for this explainer, and keep questioning the data.